Let us see these questions. During a disturbance and a synchronous, actually these are all old grade questions only, and a synchronous machine, the rotor swings from A to B before finally settling down to a steady state at point C and power angle curve. Okay, the speed of the machine during oscillation is synchronous at points. Okay, as we discussed in our starting lecture, let us consider as a, for example, simple pendulum. Okay, for example, this is a simple pendulum. Okay, is swinging. Okay, so it is swinging like this. Okay, now when acceleration will be more, when speed will be less. For example, if it is oscillating like this, now it is like this. Here the moment it is changing its direction, speed is going to be 0, and again here acceleration is going to maximum because speed is more here, maximum. Okay, and here speed is going to be 0 because you're about to, for example, it's going like this, stop and again come back. Okay, so here speed is going to be 0. Now basically when swing equation come into picture. Okay, for example, when electrical power equal to mechanical power, stable steady state condition, for example, mechanical power is there, back torque is there, mechanical torque equal to back torque, swinging will not happen. For example, mechanical torque is more than back torque, swinging will happen. Okay, so when swing equation has to be considered, okay, when it has to be considered, two things. For example, this particular pendulum, as we discussed in our first session, is on a disc. Okay, now this disc is rotating at synchronous speed omega s. Okay, and upon the disc it is oscillating, swinging. Okay, so when swing equation will come into picture. Two conditions. What are those? Accelerating torque should be there, accelerating should be non-zero, and also I repeat, and okay, speed should be other than synchronous speed. For example, speed should be, it is swinging like this. Okay, so in swinging in this direction, when it is stopped here, how much is the velocity here is going to maximum? So omega s plus this. For example, swinging from in negative direction, it is coming here. Okay, at this point, how much is this? Omega s minus delta omega s. Okay, so for example, if you think of here, this speed is going to be 0, so omega s will be there. Okay, so here speed is other than omega s. So speed should not be omega s. Then accelerating torque will be there. And one more condition is accelerating torque should be there. For example, if you see here, torque will be there, no? Okay, so there are two conditions. Anyway, point here is very simple. This is A, this is B until it will settle at C. Okay, it will swing and settle at C. What is the question they ask? The speed of them during oscillation is synchronous at points. For example, here this speed is 0, but this disc is rotating at synchronous speed. So A and B. Option A. Now let us see in this question, a synchronous generator connected to an infinite bus by two identical parallel transmission lines. This transient reactance X dash is 1 per unit for this, and the mechanical power input, it is constant at 1 per unit here, and due to some previous disturbance, the rotor angle delta is undergoing some undamped oscillations with maximum value of delta t equal to 130 degrees. Okay, so something is about to happen. Prior to that, it was already in disturbance, and in that disturbance delta t was 130 degrees. One of the parallel lines tripped due to relay maloperation at an instant delta t equal to 130 degrees. The maximum value of per unit line reactance X such that the system does not lose synchronism subsequent to tripping is. Okay, so what they have given, my delta, okay, my rotor is in swinging and maximum is 130. And here he is saying in order to become stable. Okay, so after swinging, basically system is stable. Okay, so let us consider this the machine is stable only. Let us try to solve the problem first. Okay, so see here, what is mechanical power is going to be 1 per unit. And he is saying the maximum value of per unit reactance X such that the system does not lose synchronism subsequent. In a system does not lose synchronism. In the sense, system should be stable. So let us make it as a stable and directly write the equation. Okay, like in steady state stability. But during transient, what is happening, we will do immediately after the analysis. Okay, so what is power? EF Vt by X. sine delta equal to power. Okay, under steady state conditions, kind of. Okay, in transient, what is happening actually, between 130 and how it is varying and all, we will see. Okay, so basically EF Vt by x sine delta is going to be P under steady state conditions. Now what was delta at that instant is going to be 130. Okay, EF is 1 per unit, Vt is 1 per unit. What is x in between these two? 0.1 plus x by 2 at starting. But if I remove this, it is going to be x. Okay, so what is P? 1 per unit. Okay, so this is going to be 1 into 1 divided by 0.1 plus x. Okay, so 0.1 plus x is going to be into sine delta. Sine 130 is going to be 1. Okay, so from here, if I calculate x value, that x value easily we can calculate that I got 0.666 per unit. Okay, so what is this value? A 0.67. Problem solved. Now let us do analysis. What is happening here inside? Let us see. Okay, for example, at starting, when I have these two, how much is going to be the okay, now means if I have this as x by 2 plus 0.1, my power characteristics, torque angle characteristics or power angle characteristic is going to be this. Now for example, if I remove this, then what will happen? My power angle characteristic is going to be previously it was x by 2 maximum power. Okay, so EF Vt by x, so that x value is increased or not? Increased. So my Pmax has to be reduced, so my Pmax is going to be reduced. Okay, now if you see, for example, mechanical power is 1 per unit here, mechanical power or electrical power 1 per unit here. Okay, now what happened here, before fault, before about to fault, it was already in transient condition. Okay, so it was 130 degrees. So actually before fault, in the sense before disconnecting this, my character should be upper one. Okay, in upper one, because of other disturbance, it was operating at 130 degrees. Okay, so already it was in transient, and because of because of some other disturbance, already it was in 130 degrees. Now what happened? This got tripped. So my rotor has to from 130, from here my electrical power characteristic has been changed from here to here. Okay, so it has to come down. Okay, now once it come down, what is mechanical power is more, electrical power is less. So mechanical power is more, electrical power is less, that is going to be acceleration. So it is going to be accelerating and it has to flow or it has to go, means in my electrical characteristics only or not. So this is going to be accelerating power. From here to here is going to be accelerating power. So because of that, it will try to go like this. Now once I cross this, what is happening? Electrical power is more, mechanical power is less, so it is going to be decelerating. And here they said that clearly, my system is going to be stable. Okay, means if the system is stable, under that condition x value they asked. Okay, means that my ultimately, for example, if I think of in stable conditions normal characteristic, where my operating point has to operate, it should be less than 90. More than 90, it is not stable. Under steady state conditions, he said that it is stable. Okay, means that operating point should be less than 90. In the sense, under steady state conditions, it has to settle at this point. No? Under steady state conditions. Now, let us think of acceleration and deceleration torque. So, from here, before disturbance, okay, already it was in disturbance at 130 degrees. Now, electrical characteristics came down. Operating point came down. So this is going to be electrical power, this is going to be mechanical power, it's going to be acceleration. So acceleration will come up to here. Here electrical power equal to mechanical power, but because of swing it will go like this. Now here what is happening? Electrical power is more, mechanical power is less, it is going to be decelerating and operating point should settle here. So this is going to be decelerating. Again it will cross, accelerating. So ultimately it has to settle here. Now what is accelerating power, what is decelerating power? Let us see. So mechanical power should be more accelerating power compared to electrical, okay, and electrical power should be more compared to mechanical power decelerating. So mechanical power is more, electrical power is less. This is going to be acceleration. And here in this area, my electrical power is more, mechanical power is less, so this is going to be deceleration. Okay, and if it cross this here, mechanical power is more, electrical power is less. Electrical power will be decided by electrical characteristics, so this is going to be accelerating power again. Okay, so this is accelerating, this is decelerating, this is accelerating. Okay, so anyway, they said that equilibrium criterion, only first swing we are going to consider. In first swing, if it is stable, automatically we will see it as stable. Okay, means that how much should be the x value such that this area plus this area should be equal to this area. In that way they asked x value. But anyway, why we did not consider equilibrium criterion and all in this question, though it is in transient? Because he said that it is stable. Okay, so the moment they said that stable, so electrical power is going to be electrical power equal to mechanical power equal to this only. Means that directly we calculated here, and we said that answer is 0.67. Okay, so without using transient analysis, we are able to do this calculation because they said that finally it is stable. Okay, now let us see one more question. Okay, a synchronous generator supplying active power to infinite bus via two short lossless transmission lines and is initially in steady state. The mechanical power input and the voltage magnitude E are constant if one line is tripped at time t1 by opening the CB at the two ends. Okay, at the various two ends. Yes, two ends, although there is no fault. Okay, then it is seen that the generator undergoes a stable transient. Which one of the following waveform of the rotor angle delta shows the transient correctly? Okay, first of all, let us think of, anyway they said that stable. Okay, so my whatever is going to happen means ultimately it will fall stable. Okay, so during transient time, okay, variation swinging will be there. Once transients die out, it will become stable. Now for example, in the first case what happened, this and this were there. When this and this were there, automatically Pmax is going to be more, and when this is disconnected, Pmax has to be reduced. Means mechanical power, electrical power will not change. Actually, many guys are confused. If I say Pmax is reduced, means that some people feel that mechanical power is reduced, electrical power is reduced. So no. Okay, whatever the mechanical power you are giving to the alternator, that will be decided by the prime mover, that will be converted into electrical power under steady state conditions. Okay, so for example, when these two are there, okay, these two are close, these two are there. For example, this is going to be like this. This will be there when you have L1 and L2 both. Okay, so for example, when L1 is disconnected, Pmax should be reduced or not? Yes, Pmax is reduced. Now in both the cases, mechanical power should be same, electrical power should be same. Meanwhile, transient may be there. For example, if I think of mechanical power equal to electrical power under steady state conditions, at starting what was delta 1 here? Okay, and in the second case, delta 2 should be here. Even in delta 1 case or delta 2 case, mechanical power will be same. Okay, so delta 1 to delta 2, it has to be increased. Okay, now for example, if I try to along with the swinging, right? So for example, means at a T1 disturbance occurred. So at T1, how much is this? Delta 1. Okay, after transients die out, my delta has to be increased. For example, this is delta 2. From delta 1 to delta 2, it has to be changed. So from here, swing will come. Ultimately, it has to settle down at delta 2. Which characteristic? You know it. Okay, so delta 1 means delta 2 settled. Once it is settled, delta 2 should be more. Problem is solved. Yeah. Let us take few more problems. A 3-phase 2-pole 50H synchronous generator has a rating of 250 MVA. So 50H 2-pole synchronous generator has a rating of 250 MVA. 0.8 power factor lagging. The kinetic energy of the machine at synchronous speed. In this is total kinetic energy they have given. Means that GH they have given. Okay, so the machine is running steadily at synchronous speed and delivering 60 megawatt. Okay, so under stable conditions it is delivering 60 megawatt, mechanical power equal to electrical power equal to 60 megawatt, power at a power angle of 10 degrees under steady state. Okay, if the load is suddenly removed, assuming acceleration is constant for 10 cycles, the value of power angle after 5 cycles is. So he is assuming up to 10 cycles acceleration is constant. Okay, now what is asking the power angle after 5 cycles. Okay, we have the equation previously. I told you clearly you have to remember this equation, that is going to be delta equal to delta naught plus PA by M into T square by 2. Okay, so what is T? They have given 5 cycles. Okay, so for example 5 cycles in the sense 50 H. 50 H in the sense 20 milliseconds per cycle. So for 5 cycles, 5 into 20 milliseconds is going to be 100 milliseconds, or I can say 0.1 seconds. Okay, because right, 50 H is nothing but means 20 milliseconds per cycle. Okay, this is over. Delta naught they have given power angle of 10 degrees. Okay, now you have to calculate M. Okay, so what is M here is going to be GH by pi F or 180F. Electrical degrees they have given, so this is going to be 180F. Okay, so this is MVA, megajoules per MVA, total energy, this is nothing but MVA into megajoules per MVA is going to be megajoules. Megajoules is 1000 megajoules directly they have given. So this is going to be 1000 divided by 180 into frequency is 50. Keep it aside. Now I have to calculate only PA. Now what is PA? Is nothing but mechanical minus electrical. Okay, so what is saying? The load is suddenly removed, in the sense electrical is 0. Okay, so under that condition acceleration power is nothing but Pm. So calculate delta equal to delta naught 10 electrical degrees. That's why I kept this in electrical, plus PA is going to be 60 megawatt. Okay, so 60 megawatt divided by M is going to be this value 1000 into 180 into 50 into time is going to be how much? 0.1 square divided by 2. You are going to get 12.7002. So 12.7002 degrees. Okay, or 12.7 degrees we can say. This is going to be 10, this value is going to be 2 point something. Now let us see, this problem is going to be actually very beautiful problem. A cylindrical rotor generator delivers 0.5 per unit power in the steady state to an infinite bus through a transmission line reactance of 0.5 per unit. In the sense, this is going to be generator, and this generator is being supplied to transmission line. After transmission line, infinite bus is there, and here this is 0.5 per unit. Okay, so this is going to be transmission line. Now the generator no load voltage is 1.5 per unit. Okay, and the infinite bus voltage is 1 per unit. The inertia constant of the generator is 5 megawatt second per MVA. Okay, as I continuously saying, means dimensions are very much important in stability. Okay, what is megawatt second? Megajoules only, power into seconds, megajoules. So this is going to megajoules per MVA, megajoules per MVA H. Okay, keep it aside. Now, and the generator reactance is 1 per unit. Generator reactance is 1 per unit. And the critical clearing angle in degrees for 3-phase dead short circuit at the generator terminals is, means that my at the generator reactance terminals, dead short circuit is happening. Okay, so one thing I have to say, in our previous theory sessions we have done, if you have double line circuit, under that conditions, even though fault occurs, there is a possibility of having V characteristic or kind of power angle characteristic. Okay, so there is a possibility of having power angle characteristics during the fault if you have only double circuit line. Okay, we discussed that. Okay, so if it is single circuit line, the moment short circuit occurs, total electrical power is going to come down to 0. Okay, so for example, prior to the fault, it is like this. Okay, now it is like it is operating at 0.5 per unit, 0.5 per unit under steady state conditions. Now the moment fault occurs, how much is going to be the power, electrical power, from like what do you say, generator rotor point of view, because it's going to be completely reactive only, faults. Okay, so in faults, fault current is going to be huge reactive power demanding, so it is going to be ZPF lag, we can say. So what is the output power, actual power, active power is come down to 0. Okay, so rotor acceleration, because mechanical power will be at 0.5 per unit only, but electrical power is going to be reduced to 0. So mechanical minus electrical is going to be accelerating power. So accelerating power is going to be keep on increasing. Okay, for example, here fault is cleared. The moment fault is cleared, under that condition again my x value is going to be 1.5 per unit only, so it has to go back to the same, and don't expect that it should be 90 degrees or something. Okay, let me keep here. Okay, so here this is going to fall like this, first swing, right? So first swing, if you see, my mechanical power is going to 0.5 per unit, but electrical power is going to come down. So mechanical minus electrical is going to mechanical power only, so it is going to be accelerate. And once fault is cleared, again it will achieve the same Pmax, and so this is going to be accelerating power, accelerating area, this is going to be decelerating area. Okay, so what is the angle here? This angle. Okay, so this is going to be delta max. Now let us find this angle, and what is this angle? This is going to be critical clearing angle. Okay, so what is asking the critical clearing angle in degrees for which, for a three-phase dead short circuit of the generator terminal is, means that he is asking delta CR. Okay, means that critical clearing angle. Okay, so always clearing angle should be less than critical clearing angle. Okay, so clearing angle will be decided by, as we discussed, like circuit breaker, relay operating time, everything. Anyway, this is going to be critical clearing time. Now how much is delta naught? This is going to be delta naught. Let us calculate delta naught. So what is P? P under steady state conditions is going to be EF Vt by X sin delta is going to be 0.5. How much is EF? 1.5 per unit. Vt 1 per unit. X 1.5 per unit. So 1.5 into 1 divided by 1.5 sin delta equal to 0.5. 30 degrees. Okay, so if delta naught is 30 degrees, delta naught is black only, so delta naught is 30 degrees, straight line here, so 180 minus 30 is going to be, delta max is going to be 150 degrees, right? Now let us do a small integration. So this area should be equal to this area, under that critical clearing time or critical clearing angle will come. So what is this area? Is nothing but 0.5 into delta CR minus delta naught. Okay, so directly let me take 0.5 is going to mechanical power, electrical power is going to be 0, so this area is going to be delta CR minus delta naught. Minus delta naught is 30. Okay, delta naught is 30 into pi by 180 equal to, now let us think of this minus this is going to be decelerating area. Okay, so what is this? Is going to be Pmax sin delta. What is Pmax? EF Vt by X 1, so this is going to be 1 sin delta. So let me integrate it. Okay, so 1 sin delta minus 0.5, 1 sin delta characteristic minus 0.5 is going to be this. Okay, so what are the of course d delta will come. What are the limits actually? Delta CR to delta max. Delta CR to delta maximum is 150 degrees. Okay, so this is going to be, this is going to be cos delta CR minus cos 150 minus 0.5 into 150 minus delta CR. 150 into pi by 180, minus delta CR. Problem solved. Because here 0.5 into delta CR minus into minus plus 0.5 delta CR will get cancelled. So what is unknown now? Here the left hand side 0.5, some constant. On the right hand side, constant. Delta CR has to be found. So calculate delta CR. Equal to cos inverse of something will come. I got delta CR value as 79.562. Okay, 79.56 or 79.6. Problem solved. Okay, now let us see one more problem. In this problem, a lossless single machine, actually this problem also is a beautiful problem. A lossless single machine infinite bus system is shown below. The synchronous generator transfers 1 per unit the power to the infinite bus. Okay, the critical clearing time of the circuit breaker here, see here, this is going to be CB, circuit breaker, CB is 0.28 second. If another identical synchronous generator is connected in parallel to the existing generator, each generator is scheduled to supply 0.5 per unit of power, then critical clearing time will be. Okay, so as we just now use, like, what is delta is nothing but delta naught plus PA by M into T square by 2. So if it is delta CR, it is going to be critical time. We discussed this. So what is critical time here is going to be delta CR minus delta naught. Okay, now divided by PA into M, okay, into 2 under root. Okay, so logic is very simple here. For example, if I have, for example, in the first case I have 1 per unit here. Okay, in the second case, like, 2 alternators connected in parallel, and here this is going to be 0.5 per unit it is transferring, this is going to be 0.5 per unit it is transferring. Okay, so, like, of course we discussed a bit, like, about, like, what do you say, coherent systems and non-coherent systems. So basically here, if fault occurs here, it will be coherent system. Okay, so both will swing in the same direction coherently, swinging together. Now point here is PA1 plus PA2 is going to be total accelerating power. Okay, so if it is transferring 1 per unit, if both are transferring 0.5, so what is the total accelerating? In this case, PA1 plus PA2, 0.5 plus 0.5 is 1 only. For example, in this case, what is PA is going to be 1 only. Because if electrical power is come down to 0, mechanical minus electrical is nothing but accelerating power. Mechanical is 1 per unit. Mechanical is combinedly 1 per unit. Okay, so total accelerating power in this case or in this case will not change. Okay, now what about M? Already we have seen coherent systems. In coherent systems, what was M? M equal to M1 plus M2. M equivalent equal to M1 plus M2. So, and that too, like, one thing I have to tell you here. Okay, so think properly here. Think properly. For example, if you think of M. Okay, so M, if I have some rated machine here. Okay, for example, this is X rated machine. Okay, so here this is also X-rated machine, this is also X-rated machine. Getting my point, right? So M here or M here and M here will be same. Okay, for example, just logically, if it is X-rated machine, X MVA rated machine, if it is X by 2 and if it is X by 2, then again M also can be same like PA, accelerating power. Okay, but what is happening here? This is X-rated machine means some M1. And this is also X-rated machine, same M1, same X-rated machine, same M1. So net M is going to be increased. Getting my point, right? So logic is very simple. This is X-rated MVA capacity. If this is X by 2, if this is X by 2, under that condition, critical time will not change. Okay, but what they have given clearly, see here. The critical clearing time, if another identical synchronous generator is connected in parallel to the existing generator, each generator is scheduled to supply 0.5 per unit. Means that this is X kVA or X MVA machine, this is X MVA machine, this is also X MVA machine. For example, this is supplying 1 per unit, both the machines combinedly supplying 0.5 per unit. Getting my point, right? So M, this is M, This is also m only, this is also m only. So net m equivalent will be increased. So net m equivalent will be increased, but accelerating power will be same, because 0.5 plus 0.51 and this is going to be 1, accelerating will be same. Okay, so m is going to be increased. It means that my critical time has to be increased, means that increase beyond 0.28 second. Increase beyond 0.28 second. Now one thing I have to add here. For example, for the same system, it is not coherent, but for example it is non-coherent. Under that condition, what is m equivalent? Means is nothing but 1 by m1 plus 1 by m2 whole inverse, or m1 m2 by m1 plus m2. So m1 m2 by m1 plus m2 should be less than least value of m1 m2. Okay, under that condition, for example, if a fault occurs or if a disturbance occurs such that these two systems are swinging non-coherently, under that conditions m reduce, so critical time has to reduce. Okay, so this is meant for coherent systems, because these two are connected in parallel. Beyond this, means I will tell you different conditions of coherence and non-coherence maybe in detailed course, but now it is actually difficult.